Hey, so one of you students asked about problem 4 and how to use the binomial expansion. And so part A is pretty straightforward. You take the left side and find a common denominator with the right side and manipulate some things, and it pops out to be um, what you needed to do. So I wanted to talk about part B using the binomial expansion to find the first 4 terms of the expansion of x plus 2 over 2x squared plus 5x plus 3. And so it's actually fairly straightforward application of the binomial expansion using the left side of part A. Okay, so what I'm going to do is give myself a little bit more space to write this out. But basically, what we have to do is take 1 over 1 plus x, and we're subtracting 1/3, subtracting 1 over 3 times 1 plus 2/3 x. And so let's take that and rewrite that in terms of powers, because what the binomial expansion lets us do is expand out terms that are raised to powers. So I have 1 plus x to the negative 1, and then I have 1/3 times 1 plus 2/3 x to the negative 1. And so the binomial expansion that we use is written there on the chapter review. It's this idea. I'll write it in purple. So it's the binomial color. So we have 1 plus x raised to any rational number can be expanded as 1 plus alpha x plus alpha times alpha minus 1 over 2 factorial x squared. And we can continue this alpha minus 1, alpha minus 2 over 3 factorial x to the third, etc., as far as you want to go. What you're doing is it's like a factorial on the top, and the terms of the factorial decrease until they are 1 off of the power. And so what I mean is we'll have an alpha minus 2, but we'll have an x to the third power. So if I apply that to 1 plus x to the negative 1 power, I get 1 plus negative 1x. I'll put this in brackets so we can tell this is just the first piece. Plus, then I do negative 1 times negative 2, because I subtract 1, over 2 factorial x squared. And this problem wanted us to just go up to the x cubed level and then to stop. And so I'll go to the x cubed level. Then you do negative 1 times negative 2 times negative 3 over 3 factorial x to the third. We could continue this process for as long as we want. Minus 1/3 times the same sort of expansion, except instead of x, it's 2/3 x. And so I can really copy down a lot of the same pieces that I just figured out on the left side. So negative 1 times negative 2 over 2 factorial 2/3 x squared, and etc. We can go negative 1 times negative 2 times negative 3 factorial 2/3 x cubed. Sorry, always run out of space. And then, because the question only asked for us to do it up until the x to the third term, we're just combining like terms at this point. And so when you look at it, we have the first term is positive 1 minus 1/3 of 1. So our first term is 2/3. Then our next term is negative 1x. Here we have negative 2/3 x, and it is a negative 2/3 multiplied by a negative 1/3 in front of the brackets there. So that's a positive 2/9. So we have negative 1 plus 2/9 would be 7 over 9x. Then on our x squared term, we have 1 times 2 over 2 factorial. That cancels out. So you have an x squared. Over here, we have 1 times 2 over 2 factorial. That cancels out. But we have 2/3 x squared. The squared should be outside of the parentheses. And so 2/3 squared is 4/9 times the negative 1/3 means it's negative 4/27. So if you have 1 minus 4/27, you get 23/27 x squared. Okay, now we're moving on to the next piece, the x cubed term. The factorials cancel out, but there's a negative piece there. Same idea here. We have the factorials canceling out, but we have the negative piece there. So we have a negative 1 x cubed. Over here we have 8 over 3 to the third power. So 8 over 27 times another negative 1/3. So that would make positive 8 over 81. So we have negative 1 and positive 8 over 81, which makes negative 72 over 81 x cubed. I believe I made a small mistake here with the 7/9. That should be a negative 7/9. Should be a negative 7/9 because we had a negative 1x, and darn it, I lost it there. But that second term should have been a negative 7/9. So that's our pattern right there using the general binomial theorem. Please ask more questions if you need.